Hey everybody, we're here live again with another office hour. Again, I'm partnering with Chegg to bring you Organic Chemistry 1 office hours every Tuesday at 5 p.m. Pacific time. Check the QR code in the top left corner of the screen if you want to see the other topics that Chegg is offering office hours for. You got math, you got all kinds of different topics. We're here to help you get through all of your courses this semester. Again, I'm covering Organic Chemistry 1 content. So if you're watching along in the chat, please provide your questions. If you have any questions, keep them Organic Chemistry 1 related. They can be about the questions that I have prepared that I will go over with you, or they can be other Organic Chemistry 1 questions that are not related to the questions that I'm going over. Anything that you have, I'm here to help you guys. So yeah, any OChem questions that you have, feel free to throw those into the chat. Great. Okay, so let's go ahead and get started. So let's go over, I put a few addition reactions in this one because we've been doing other stuff, other types of reactions, but addition reactions are a very, very large class that are important for Organic Chemistry 1. So let's recall some of these. So we have right here a hydrohalogenation. So we need the starting material. We've done this here, okay? And so we have done a hydrohalogenation. And what do we have here? We have hydrogen peroxide. And we know that peroxides are going to promote anti-Markovnikov regiochemistry. So if we did anti-Markovnikov hydrohalogenation, that means that the bromine atom went to the less substituted of the two participating in the pi bond. Just make some room here. So the question is, this was an addition reaction. So the starting material had a pi bond somewhere. Now the question is, where was the pi bond? So certainly the carbon that bears the bromine has to have been one of the two carbons in that pi bond. But the question is, which one is the other one? So this carbon has to be participating in the pi bond, but is the pi bond here or was the pi bond there? Now, if we know that the bromine went to the less substituted of the two, that gives us our answer, right? So we're going to go like this. And this is a secondary carbon. This is a primary carbon. This is a tertiary carbon. For the bromine to have gone here and for that to have been the less substituted carbon of the two, the pi bond has to have been there. I can do that better. Okay. So this is a secondary carbon. Here, this is a primary carbon, this is a secondary carbon, and this is a tertiary carbon. And that's why anti-Markovnikov hydrohalogenation put the bromine on the less substituted secondary carbocation, secondary carbon. So that's what we're doing. We know that it is anti-Markovnikov, and we're just comparing the substitutions on these carbons to discern where the pi bond was in the starting material. So it turns out it is that one. Let me see if I missed anything. Pi Trader asks for aromatic substitution. I don't know if I have any on this one. If you have a specific one, you can toss that in the chat, or you can ask for a specific reaction, or something about different orthometa pair directors or something like that. And I can try to maybe I can make up a question on the fly. Okay. Let's go to the next one. So last time we did a couple of Newman projections, and I think it's good to always practice those a little bit. So let's do a couple more Newman projections here. So we have this compound, and we have we're looking down this bond. So here's our eyeball, right? We're in the screen, and we're looking down this bond right here. Right? We're looking down that carbon-carbon bond. And so we're going to draw what we see. And so the three groups that are projecting from this front carbon right here, those will begin at the center there. And so what do we see? We see straight down, we have CH2OH. So we can go like that. You can also write CH2OH if you prefer. Doesn't matter. So that is so that's straight down because that is in the plane of the screen as well. We're in the plane of the screen from that perspective, and that is also in the plane of the screen. Now we have the hydroxyl on the wedge bond, and from that perspective, if we're to the right of the molecule, then the wedge bond is going up and to the left. So we have to put an OH right here. We'll write HO. Remember, it's important. We want the oxygen to be on the other side of this bond, not the hydrogen. So we wouldn't put OH, we'll put HO so that the oxygen can be right here, showing the covalent bond between oxygen and carbon. And then we have an implied hydrogen up and to the right. So that's the front carbon. And now we can also see the groups projecting from the back carbon. So we can't see the back carbon or the bond leading to it. It's obscured by the front carbon, but we can see what is connected to it. And so that's why the bonds on the back right there. So going straight up, we have an ethyl group. So boom, boom. You can also write CH2CH3. So that's straight up because it's also in the plane of the screen along with us. And then if the wedge bond is going down into our left from the perspective of being in the screen, it's down into the left. So we have to put the fluorine there. And then we have a methyl group there. So that is our Newman projection for that bond. We can see everything is staggered. We don't have any gauche interactions between alkyl groups. That's where everything is going to sit. Okay, let's do one more. We've got this one here. So we are sitting in the screen right there, looking down this bond right here. So what do we see? We are in the plane of the screen, and so we see the bromine straight down, also in the plane of the screen. So there is the bromine. And then now, see, so this is very important. We definitely don't want to memorize wedge bond left, dash bond right, or something like that, because it depends on your perspective. So when we were on the right side of the molecule, the wedge bond is going to our left. But now that we're on the left side of the molecule, the wedge bond is going up and to the right. So it depends on your perspective. These are definitely a lot easier if you have really good spatial reasoning skills. So if you can, in your mind's eye, place yourself in the plane of the screen, and then just in your head observe, you can see that the hydroxyl is going up and to your right. That is a great advantage. Now, not everybody has that ability. So whatever tricks you want to come up with, you could do flashcards and say, if I'm on the left, then the wedge bond, if I'm on the left of the molecule, the wedge bond is to my right. You can do that. There are memorization ways of doing it. But definitely try your best to harness those spatial reasoning skills. See if you can place yourself in the plane of the page or the board. So we've got the OH up and to the left, and then we have an implied hydrogen up and to the left. Hydroxyl up and to the right, implied hydrogen up and to the left. Now we cannot see this carbon-carbon bond or the back carbon. They are obscured by the front carbon, but we can see what is connected to that back carbon. So we have a bromine going straight up. Then we have the iodo group down and to the left, right? If we're inside that screen there, the dash bond is further away than the screen from this current perspective looking down. And so that will be to the left from the perspective of in the screen. So there's the iodine, and then we have an implied hydrogen going down to the right. So that's this one. A little bit about some of the terminology. Again, this is staggered. If these groups were on top of each other, such that the dihedral angle was 0, that would be eclipsed. That would be an eclipsed formation. The dihedral angles being 60 degrees make it a staggered conformation. And then just some other terminology. We could say that, for example, these bromines are anti to one another. When you're talking about a 180-degree dihedral angle, that is called anti with respect to one another. It's relative terminology. So just a little review on Newman projections. That is good stuff to know. Data VFX, why aren't the BR and OH 180 degrees from each other. Let's see. So I think you're talking about the second one. So you're asking why this OH and this Br are not 180 degrees. So we're just drawing the configuration as shown. Don't forget that sigma bonds, carbon-carbon sigma bonds, are always rotating. So it's not fixed in this configuration, in this conformation, right? The conformations are constantly changing. If there's as long as there's sufficient ambient heat energy, it is going to be constantly rotating through these conformations, and they're not all of the same energy. All of the staggered conformations are lower energy than the eclipsed conformations, and you may be right. I'm actually not sure which no, to be honest, I think that the bromines anti to one another is the lowest energy conformation, just because of the radius of the bromine atom. It's so much bigger than an oxygen atom, because it's several periods down from oxygen. But yeah, so that this bond is rotating all the time, and it is experiencing each of those conformations for a discrete period of time. It'll spend the lower the energy, the lower the energy associated with a particular conformation, the more time it will spend in that conformation. A very high energy conformation, it will spend very little time in it, right? That's why it passes through the eclipsed conformations only on the way to staggered conformations. But I believe this is the lowest energy conformation. I think that's the case. Brett Rhodes asks, what is the purpose of doing a Newman projection when standard model already shows angles? So, I mean, it kind of does, right? The angles and the spatial relationship is implied by dash bonds and wedge bonds, but this makes it very clear. Right here, we can see the difference between the dash bond and wedge bond, not just as a symbol, but as actual spatial orientation in the direction that the groups are pointing. So it's just it's a different way of depicting something, depicting the molecule in 3 dimensions. Right, we're going into the plane of the screen and looking at it from the side and depicting what we see when we do that, as opposed to a top-down view. So it's just another way of looking at a molecule. Data VFX. So the diagram is not a snapshot. It kind of is. It's a snapshot in the sense that it is not permanently fixed into that conformation, right? Once again, all these sigma bonds are constantly rotating. So, like, even over here, this sigma bond is rotating. This sigma bond is rotating. This sigma bond is rotating. It's sitting in all of these conformations for a certain amount of time as it cycles through them, in an effort to get to the lowest energy possible. So, okay, that's it. All right, back to a couple addition reactions. So once again, we want to provide the starting material that would yield the following product. So now what do we have? These are the conditions for hydroboration oxidation. And so this is anti-Markovnikov hydration. So that part is memorization, right? We have to memorize that these reaction conditions indicate hydroboration oxidation, and we have to memorize that hydroboration oxidation, it promotes anti-Markovnikov hydration. That's all that we have to memorize. After that, we're just applying our understanding of what those words mean. So hydration means, so once again, this is an addition reaction. So this came from, this had a pi bond, right? There was a pi bond somewhere. And what we're saying is that we added an H and an OH to one to each of the 2 carbons that were participating in the pi bond. And we added the hydroxyl to the less substituted, right? So anti-Markovnikov regiochemistry indicates that the more important group is going to the less substituted carbon that was participating in the pi bond. So in this case, that would be this. And Yeah. Oh, and it's the same no matter which way we point that methyl group there. So that's fine. So this makes sense. And you can always check yourself by going in the forward direction, right? We have a tertiary carbon and a secondary carbon. And then this one's primary, just to be clear. And so if the pi bond is in between the tertiary and secondary carbon, then the hydroxyl will go to the secondary carbon and will get the desired product. Right. That's why the pi bond cannot have been in between the primary and secondary carbon, because if it was, then the hydroxyl would be on the primary carbon, not the secondary, which is not the indicated product. So once again, all we're doing is we're looking at the reaction conditions, and we recognize that we're doing hydroboration oxidation. What's the tip off? Hydroboration. Well, we've got BH3 that's got boron in it. That's how we're going to remember hydroboration oxidation. And then how do we memorize that indicates anti-Markovnikov regiochemistry? That's the peroxides. Peroxides are the classic anti-Markovnikov promoters. They're going to cause addition reactions to go anti-Markovnikov regiochemistry. So that part is memorization. Might need to do flashcards, but after that, we know what these words mean, right? We know what is implied by these regiochemical terms, the stereochemical terms like syn and anti, etc. And we know what hydration means, H to one carbon, OH to the other. So yeah, that's that one. Lyrit, yes, these streams are all on my channel. You can go to the live tab and you'll see about a dozen live streams that I've done so far. So you can check what other types of problems I've been covering. Propylene says, is Karash effect and anti-Markovnikov the same thing? I have never heard that term, Karash effect. That is new terminology to me. So I'm not sure that it would mean the same thing. Anti-Markovnikov and Markovnikov are very particular terms that refer to the regiochemistry associated with a particular addition reaction. So I'm not sure what that means. Grish asks if I'll do Orgo 2. So addition reactions are pretty firmly Orgo 1, but some of the stuff I've been going over, it depends on what course you're in. On some organic chemistry 1 syllabi, you are covering Grignard and enolate chemistry and nucleophile or electrophilic aromatic substitution, etc. Some of the stuff I've been covering. Some wait till OChem 2 to do that. So it really just depends on the particular institution. Nikolai asks, can you explain reaction mechanisms? I do have one reaction mechanism on this one. It's for radical chlorination. But if you have another mechanism that you are interested in going over, let me know. I can try to toss that in there as well. One thing I've data VFX. One thing I've never understood: do these diagrams show bond between single elements or atoms? So chemical bonds are covalent bonds are between atoms. Elements are just types of atoms, right? Carbon is an element, but in a molecule you have individual carbon atoms. So a little bit different. Okay, let's do the next one. So draw the product of the following transformation. So we have this cycloalkene, and we're doing hydrogenation over platinum metal. So this is hydrogenation. And so if we're doing this over platinum metal, this is going to be a syn hydrogenation, because this is an example of heterogeneous catalysis. So you have a solid metal catalytic surface, and the hydrogen molecules migrate towards that surface. That promotes the cleaving of the hydrogen-hydrogen bond, and now all of a sudden you have hydrogen atoms sticking off the metal surface like this. Then what happens is the substrate approaches, and then the hydrogen atoms add to the double bond, directly from the metal surface. So because of the heterogeneous nature, it has to be syn, because both of the hydrogen atoms they must be added to the same side of the molecule because they're coming from the same solid surface. There's no way for one to add like this and then the other one to come from the top. They're both stuck to this metal. So the substrate approaches and then the two hydrogens attach like that. So because the two hydrogens are added in syn fashion, they must be cis on the product. And that means that any substituents that are already present on the carbons that are participating in the double bond must also be cis to one another in the product. And so we get this. Here is our 5-membered ring. And so we can go either way. I'm just going to put the methyls on the dash bonds. Could also be on the wedge bonds. Identical molecule. And if we need to, we can also draw in the implied hydrogens, right? Just to be clear about what happened. So we don't have to draw them because they are implied, but these are the hydrogens that we added, and they were added to the same side of the molecule. So that means we went from sp2 carbons, trigonoplanar sp2 carbons, to tetrahedral sp3 carbons. So we had to have dash bonds and wedge bonds now. So the hydrogen atoms that we added are on the wedge or the dash, either way, and then the methyls get pushed to the other side. So that is syn hydrogenation. Hydrogenation over platinum metal is syn hydrogenation. It's an example of heterogeneous catalysis. Blood rose. Yes. So yeah, anti-Markovnikov addition reactions tend to proceed by radical mechanisms. That's correct. Cool. That looks good. Okay, so moving on from addition reactions, let's take a look at some electrocyclization. So the classic is the Diels-Alder. So we want to provide the starting material that would yield the following product. So we know that Diels-Alder reactions generate 6-membered rings, right? We know that we're going from a diene with 2 pi bonds and a dienophile with 1 pi bond to a 6-membered ring that contains 1 pi bond, because the 2 pi bonds in the diene, one of them remains a pi bond, while the other pi bond in the diene and the pi bond in the dienophile become sigma bonds to close up that 6-membered ring. So when we're doing retro Diels-Alder, the first thing we need to do is identify the ring that formed. Okay. And so the ring that formed must be this one, the one on the right, because it's got the pi bond in it. So it can't be this one over here. We've got to have it be this one. And so let's break these. And so if we do that, we can let's go backwards with these. So, okay, I'll get rid of the squiggles there. So this sigma bond can go there, this pi bond can go there, this sigma bond can go there. And these are, this isn't in the forward direction. I'm undoing the activity of electrons that went in the forward direction in order to go backwards. And so what we're saying here is that we had this. That and that. And so this is where those pi bonds were. And this. So a couple of things, right? If we're doing this, we're cleaving these bonds and pulling those fragments apart, right? And then one other thing, these methyls are cis on the product, so they must be cis on the dienophile, right? That is a cis alkene. Were they trans, if this was one on the wedge bond and one on the dash bond, then they would have been trans on the dienophile, right? This way and this way. but they were cis. So it's like this. And we can even test this by going in the forward direction, right? If we here are some dashed lines for where the sigma bonds are going to go, we could go like that and like that and like that. And we would see that we would get this product in the forward direction. So Diels-Alder will always yield a six-membered ring. So if you're going retro Diels-Alder, identify the six-membered ring that can have formed and go backwards. And that's it. Not related, but Shan asks, why is root 2 irrational, but pi is real? So they're both real. They're both real and both irrational, right? Irrational means the digits go on forever. So root 2 and pi are both irrational and real numbers. Golden asks, can you learn chemistry from scratch? You certainly can. Watch my general chemistry playlist and then organic chemistry and then go from there. Two correct. Jimmy says two correct answers. That's actually true, I guess, because yeah, I guess we could have severed these ones. Yeah, we could have pulled that apart and it could have just been ethene. Yeah, that's actually true. Good call. Okay, let's do one in the forward direction now. So here's our Diels-Alder. Okay, so this is going to be a little tricky. Put that going over there. Put that going over there. And then we're going to go, this pi bond remains a pi bond right there. This pi bond becomes this sigma bond. This pi bond becomes this sigma bond. So this can get a little bit convoluted, but you just kind of have to work with what you have. So, okay, the first thing you always want to do when you draw the Diels-Alder product is draw the six-membered ring that formed, right? Start there, and then everything else that's connected to it, you can get that next. So here's our new six-membered ring, okay? Now, so which are the carbons that are participating in that six-membered ring? The carbons that are participating in the new six-membered ring are the six carbons that were participating in the three pi bonds that shuffled around. So this one, this one, this one, this one, this one, this one. Those six carbons are the six carbons in the new six-membered ring every time, okay? So now what else is there? So this pi bond went right here, and so we have a pi bond there, right? These two pi bonds became sigma bonds. This pi bond became this sigma bond right there, and this pi bond became this sigma bond right there. So now what else? Now we have two methyls here, so those didn't go anywhere. Those have to still be there. So those are two methyls, and they can stay flat because these are still sp2 carbons. Right, all for so this carbon became sp3, this carbon became sp3, but these two right here remain sp2. They were each participating in one pi bond, and now they're participating in one pi bond with each other. So they are still sp2 hybridized. These methyls are now flat. Now what else? We have these other two carbons. So when the diene is already cyclic, that ring doesn't break. Right, those carbons have to still be there. So we make this bridgehead there. There's a bridgehead carbon leading to a two-carbon bridge. We can make that a little thicker. And so that looks like this. So we're shading this in to indicate that those two carbons are sticking up. They're sticking up out of the screen towards us. Right? So this is a bicyclic product. We have carbons that are participating in more than one ring, right? We've got this ring here and this ring here. So four of these carbons are participating in two different six-membered rings. So it's a little funky. Now over here, we have two carboxyl groups And because the carboxyl groups are trans to one another on the dienophile, they're going to be trans to one another on the product. So we're going to put a wedge bond here. And there's a carboxyl group. And then we're going to put a dash bond there. And there's another carboxyl group. And we have to acknowledge that we're going to get a racemate here. We're going to get a racemic mixture because we could have the wedge bond up here and the dash bond down there, or the dash bond up here and the wedge bond down there. And those would be different molecules, right? There's no internal symmetry there that would render those two the same thing. So those are two different stereoisomeric possibilities. So once again, for drawing Diels-Alder products, there's a lot. I find that a lot of students get confused when there's extra stuff, but don't let the extra stuff confuse you. All you need to do, identify the 6 carbons that are participating in the pi bonds that are being cyclized. And those are the 6 carbons that are in the new 6-membered ring. So draw the 6-membered ring, recognize that those are the carbons that are in the ring, and then just draw everything else that's there, right? You showed the new chemistry. So now just show what else is there. We had the pi bond. One of the pi bonds remained a pi bond. Draw that. We have these 2 methyl groups. Those are still there. Draw those, and those are flat. Then we had the carboxyls on the dienophile. So draw those and make sure they're trans because they're trans to one another on the product because they're trans to one another on the dienophile. And then, of course, the most confusing part for some students, those bridgehead carbons, those have to still be there. So they did not participate in the cyclization, but they are still there. That original 6-membered ring is still there. There's just also a new 6-membered ring from these 4 and these 2 carbons. That's what the Diels-Alder is. So there's your Diels-Alder product. Okay. Oh, is endo or exo favored for 6? So yeah, Jimmy asks. So in this case, there would be no difference, right? There's no energetic. We're talking about a pair of enantiomers, and so there's no energetic difference there. What would be different is if they were both dash or both wedge. If they're both dash or both wedge, as drawn here, more often than not, both being on the dash, I believe, is better. So typically the endo configuration is more energetically favorable because what ends up happening is that in the transition state, there's pi electron overlap. There's interaction between pi electron density that stabilizes the transition state. So that's when you have the diene and then the dienophile overlapping under there, right? It's under there. And so as this approaches like this, there's favorable pi-pi interactions as opposed to exo would be like this. If it's approaching and the functionality on the dienophile is jutting away from the diene, and so those end up like that. That doesn't give that favorable overlap that stabilizes the transition state. So typically endo is favored energetically, thermodynamically. There are counterexamples to that, however. So okay. All right, let's go to the next one here. So let's check out some enolate chemistry. So we want to draw the product of the following transformation. We have propanal, and we have 2 equivalents compared to hydroxide. So this is just telling you it's going to react with itself, right? So we're going to enolize and then do some aldol here, aldol condensation. So we've got hydroxyl. So we've got a strong base, means we're probably going to do an acid-base reaction. So we want to find the most acidic proton on the aldehyde. So where is the most acidic proton? It's not the one on the carbonyl carbon. It is actually the one, and there's 2 of them here, so we'll draw both of them. So remember that the protons that are alpha to a carbonyl are mildly acidic, weakly acidic, around pKa 19, which is just acidic enough to react with a very strong base like hydroxyl. We are going to grab that proton. Those electrons go to form this pi bond here, kick that pi bond up onto the oxygen, and we will get our enolate. So whoops, missed a carbon there. So there is our 3-carbon enolate. And so enolates are source of nucleophilic carbon because we have another resonance structure there. One of the resonance structures involves a formal negative charge on carbon, right? And so if you have negatively charged carbon, that's nucleophilic carbon, right? Carbon ion can go and attack something. So what can this attack? What can a nucleophile attack? Do we have any electrophiles hanging around? Well, carbonyl containing compounds are electrophiles. So an enolate can attack an aldehyde, and it will attack the carbonyl carbon. So how are we going to do this? Let's do it like this. Let's have this, and so you can go from either. So you can go like this and like this, right? You can attack that way. Since this resonance structure is right here, I'm just going to use this one. Either one is absolutely correct. And so we're going to go like this, and we're going to go that, hit this, and we're going to go like that. So what did we do? This is the new carbon-carbon bond that we just formed, okay? This electron pushing arrow right here is now represented by this right here. So what we need to understand is we had a 3-carbon enolate, and it was the middle carbon that was doing the attacking. So the carbonyl reforms, if you're using this resonance structure, right, this comes down like that. So we're reforming the carbonyl, and then it's this middle carbon that's doing the attacking, but that outermost carbon is still there. So that has to still be there, right? A lot of times I see students just omit that carbon. We don't want to forget that, right? We didn't gain or lose any carbon content. We just formed a new carbon-carbon bond. So that carbon's still there. And then we attacked what was the carbonyl carbon, right? This used to be a carbonyl right here, but that this carbon attacking right there caused the pi bond to go up onto the oxygen. So we've got our oxyanion. And then we can, this is aqueous. So let's just grab a proton from water. And we're here now. And then we've got more hydroxide in solution. So we can go again, right? This proton right here is just as acidic as back here, right? It's still alpha to the carbonyl. So let's go ahead and grab it. And now, so this was the aldol addition product. Now we're going to go ahead and do the condensation. The second step is the condensation. Condensation meaning we lose a water molecule, not an intact water molecule, but H plus OH, right? We lose this hydrogen and we lose this hydroxyl. And there is our aldol condensation product. So a lot of students will ask, wait a minute, I thought that hydroxyl is a terrible leaving group. And that's absolutely true, but we are in very strongly basic conditions. So we have a lot of hydroxyl, hydroxide ions. We have many hydroxide ions floating around in solution. So one more is not going to hurt. In strongly basic conditions, hydroxide is a perfectly reasonable leaving group. So this is the aldol addition product. Then we did the condensation. So we could, a condensation we would summarize as minus H2O. And once again, when we say minus H2O, what we mean is H plus OH. That's what that is. So That is the aldol condensation. So once again, we had our 3-carbon aldehyde, strong base, got one of these alpha protons around pKa 19, form the enolate, take one of these resonance structures of the enolate to attack another equivalent of the aldehyde, kick that pi bond up, we get our oxyanion. This is the new carbon-carbon bond we just formed to generate a larger carbon skeleton. Protonate that oxyanion with the water, and then another hydroxide can come along, grab the other proton at that alpha position, form that pi bond, kick off the hydroxyl, and there is our aldol condensation product. So an aldol addition product will have a carbonyl, because the carbonyl reforms, right? The enolate will reform the carbonyl when it attacks the other carbonyl, right? So this carbonyl was part of the enolate. So an aldol addition product will have a carbonyl and then a hydroxyl beta to the carbonyl, right? Here's the alpha position, here's the beta position. It will specifically have that spatial orientation, because the carbon alpha to the carbonyl in the enolate is going to act as the nucleophile, and it will attack the carbonyl carbon. The carbonyl carbon is the electrophile. So that must be the spatial orientation of the two oxygen containing functional groups. They have to be beta. The hydroxyl has to be beta to the carbonyl. And then the aldol condensation product will have a carbonyl, and then it will have an alpha beta degree of substitution. So here's the alpha, here's the beta carbon. That is where the pi bond must be. So if you see a compound that has a carbonyl and then an alpha beta degree of substitution, an alpha beta degree of unsubstitution relative to the carbonyl, you know it can have formed via aldol condensation. Okay, so that's a little bit of enolate chemistry. Sometimes we do aldol, sometimes we do Michael addition, sometimes we do Robinson annulation, sometimes we do Claisen condensation, sometimes we do Dieckmann condensation. There's a lot of different ways of doing this enolate chemistry. It just depends on what the enolate is. So like, for example, for Claisen condensation, that's when you form an enolate out of an ester as opposed to an aldehyde or ketone. But mechanistically, it's not that different, right? It's just enolization, and then the enolate attacks a carbonyl containing compound, whether it's an aldehyde, ketone, ester, whatever. So it's a little daunting at first, but once you get just the basics down, it's really just that every time. Let's see if I missed anything. Counter examples, not sure. Counter examples in counter example. All I said. Oh yeah, I just mentioned that sometimes exo can be favored over endo. I think maybe sterics might be the main reason. I'd have to look that up, but off the top of my head, so I was saying that for Diels-Alder, endo tends to be favored because in the transition state, so if the diene is coordinating to the dienophile here, and there's pi electron density that is on the diene and the dienophile, and there can be an overlapping stabilizing effect, as opposed to exo, where this part of the dienophile is sticking out over here away from the diene. If the dienophile is very bulky, I believe that will help promote exo, just because of the steric hindrance associated with them approaching each other. But I'd have to look that up to verify. I know that, and I'm pretty sure that endo tends to be a thermodynamically favored product, whereas if it's exo, it's kinetically favored. I'd have to double check that, but I believe that is the case. Devil Mark is asking for some EAS questions. So I did a bunch of those last week. So if I don't get to any, check for the past 3 weeks or so, I've been doing a lot of EAS. So if I don't get to any today, just go to my live tab and check some of the previous live streams, and you will get a bunch of those. Rotund Rabbit said, "Can you explain counter ions?" So yeah, like I mean, okay, so like so potassium hydroxide, right? We have hydroxide, and then the potassium cation would be the counter ion, right? And then, sometimes you can have a situation where a carbonyl is reduced, and then you have a counter ion hanging out because it's in solution. I'm not sure exactly what you were asking for, but if you just meant what is a counter ion, we're just talking about an oppositely charged ion that's coordinated to whatever ion you're talking about. Jackson asks, in the E1 reaction of, whoops, in the E1 reaction of 2-bromo 2-methylbutane, is TS2 lower for the anti-Zaitsev alkene? So I assume you mean the Hoffman. Um, oh, whoops, sorry, butane. Yep. Boom. Okay, so we're saying that if it's E1, we went like that, and oops, and then we have this. And so you're asking, is the transition state lower for the Hoffman elimination versus the Zaitsev elimination? Yes, it is. And that discrepancy is magnified depending on how bulky the base is. So if you have tert butoxide, let's say, then the discrepancy in activation energy is significant enough to pretty much exclusively promote the Hoffman product. Right. So the bulkier the base, the more likely you're going to go Hoffman. If you had just a hydroxide ion, then it's so small that the steric hindrance associated with approaching the internal section of the molecule as opposed to the periphery, it's still there. It's still going to have a lower activation energy going to the edge of the molecule. It's just a difference that's not significant enough to dissuade the thermodynamically favored pathway of going Zaitsev, which would give the internal alkene there. So yeah, hope that helps. Okay, let's do the next one. Let me erase some stuff here. Okay, draw the complete mechanism for the monochlorination product. So radical mechanisms are a little funky for a lot of OChem 1 students. So there's a few discrepancies between radical mechanisms and the typical mechanisms that we go over. So the first thing we want to understand is that every radical mechanism has it begins with an initiation step. So the halogen bond, there's a few types of bonds that readily undergo homolytic bond cleavage. Halogen bonds do this. Also, oxygen bonds, such as those found in peroxides. That's the reason that peroxides promote anti-Markovnikov regiochemistry, but that's not related to this right now. I'm just saying that oxygen bonds and halogen bonds, they're sufficiently low energy that it's easy for them to cleave homolytically. You need either a photon of a particular frequency, or in some cases even just heat. If the temperature is high enough, they'll spontaneously cleave. Notice that I used single-headed electron pushing arrows, not double-headed. Double-headed signifies the motion of two electrons, like the two electrons in a covalent bond or in a lone pair, etc. This signifies the activity of one electron. So that is going to give us two chlorine radicals. We denote radicals with these single dots kind of like just a Lewis dot structure, but we don't need to draw the other six electrons. We understand that there's an unpaired electron. So radicals are species with unpaired electrons. So the chlorine radical is going to now come over here, and so the thing about this is that there are 12 identical methyl protons. There's no proton on the central atom, that's on the central carbon. That's a quaternary carbon. There's no hydrogens there. So a chlorine radical is going to approach this substrate, and it sees 12 identical hydrogen atoms. So it doesn't matter which one we get. But so let's take a chlorine radical here, and what we're going to say is that goes there, that goes there, that goes there. Again, all single-headed arrows. So there is our primary radical. And we've also made some HCl byproduct. Okay. Now that we have an alkyl radical is unstable, especially a primary alkyl radical, and that is going to react. Let's just draw this separately. It's going to react with pretty much whatever it finds first in solution. However, chlorine radicals are difficult to form. That's the endothermic step, right? That's the unfavorable step, the homolytic bond cleavage to generate the radicals in the initiation step. So the most likely species for this to encounter is going to be just another molecule of chlorine, diatomic chlorine. So let's do that. So we're going to propagate another chlorine radical. So there's another chlorine radical. That chlorine radical can go and then can facilitate another reaction, generating another chlorine radical, facilitating another one, etc. So these are the steps to get to our monochlorinated product. I specified monochlorination because it wouldn't necessarily stop there, right? We could chlorinate again. We could chlorinate again on the same carbon. We could chlorinate on a different carbon. We could keep going until there are a bunch of chlorine atoms on this molecule, but mechanistically it'd be the same every time. Mechanistically, we would either be generating another chlorine radical from another initiation reaction, or we would just be taking a chlorine radical that was propagated from an earlier step. And then the chlorine radical is interacting with a hydrogen atom, generating HCl byproduct and generating another alkyl radical. So that can just happen over and over again. But what we're understanding is we've got an initiation reaction, right? That is going to be endothermic. Initiation reactions are always require energy, right? Those are going to be endothermic. So that's how we get the chlorine radical. The chlorine radical will react with a particular carbon-hydrogen bond, generating an alkyl radical. So we're propagating. That's a propagation step. Propagation steps are always covalent species plus radical species yield some other covalent species and some other radical species. So we have the chlorine radical. We're generating an alkyl radical. We have a covalent a hydrocarbon. We're generating covalent HCl. So that's how we get the alkyl radical. And then the alkyl radical is most likely to react with diatomic chlorine. It wouldn't be wrong if you drew this as a termination step. You could have this interacting with a chlorine radical to just do a termination and just get the product, and that would be exothermic, right? Termination is when two radical species interact to form one covalent species. It's the opposite of initiation. One covalent to two radicals. Termination is two radicals to one covalent. Okay, so you could have drawn it that way. It's just statistically much, much less likely. The alkyl radical is way more likely to run into diatomic chlorine in solution than a chlorine radical. So that's it. We've got an initiation step and two propagation steps to get to the product. That is our monochlorination product. Here, we didn't have to worry about regiochemistry because there was no other type of carbon for it to go to. But a bit about the regioselectivity of chlorine radicals. The regioselectivity is very low. Chlorine radicals will just go almost anywhere on a hydrocarbon. Bromine radicals, on the other hand, are highly regioselective. You will almost exclusively get radical bromination on the most substituted carbon because that proceeds via the most substituted radical intermediate. So that is the reasoning there. Yeah. So that's it. The Orioritz asks, "Does this problem have a limiting reagent?" It certainly can. I mean, you could provide that information. It I mean, you could limit it however you want. You could limit it by adding only not that much chlorine if you wanted. That's not specified here. That's more of a Gen Chem concept where you're given actual numbers that you need to calculate. Yeah. So let me know if you have any other questions. I'm reticent to move on to this NMR one because it's going to take more than 4 minutes. So I don't really want to start it because I won't be able to finish it. Tell you what, earlier someone asked for an EAS reaction, so let's just do one of those. I'll make it up. Let's say that we've got this guy and we've got this guy, and we're going to do chlorination. We just did radical chlorination, so let's do chlorination on in the context of EAS. So just off the top of my head here, right, we need to memorize all, right, there's conditions for chlorination, bromination, nitration, alkylation. There's different types of EAS reactions we can do. And when we do them on monosubstituted aromatic compounds, we have to consider the directing effects of the functional group that's already on the molecule. So here we have this carbonyl containing functional group. This is going to be a meta director. It is a meta director because it is electron withdrawing. Because when you have so it's by resonance, right? This pi electron density can get pulled up into that carbonyl by resonance. Very important, though, it's only when the carbonyl is adjacent to the ring. If we had a several carbon chain and a carbonyl was further down the chain, then that would not have that effect, right? That wouldn't be the case anymore. It's only that it's adjacent. So we have this carbonyl here. That makes it a meta-directing group. So that means that whatever the incoming electrophile is, doesn't matter what it is, it's going to go meta to the already existing functional group. So we don't care about the identity of the incoming electrophile. It is the functional group already present on the molecule that directs the incoming electrophile to a particular position. So we would end up with this. And we're going to put the chlorine there. Okay. So remember, this is called the ipso position. The carbon that bears the functional group is ipso. This is ortho. This is meta. This is para. This is also ortho. This is also meta. So there are two ortho positions, two meta positions, one ipso, one para. And meta directors direct incoming electrophiles to the meta position because that pathway avoids placing the positive charge in the uranium ion intermediate directly adjacent to the electron withdrawing group. Having a positive charge, a form of electron deficiency, next to an electron withdrawing group that withdraws even more electron density away from an electron deficient intermediate is very unfavorable, energetically unfavorable. So avoiding that most energetically unfavorable position or pathway is going to be the best. So it goes meta to avoid that. whereas electron donating groups are orthopara directors because in such a condition they stabilize that positive charge. So I talked about this in a lot more detail in some of the other live streams, so go back and check those if you want more info. Otherwise, I believe that is it. Let me see. It specifies monochlorinations to Cl2 is limiting. I mean, yeah, if you have a limited amount of Cl2, it could monochlorinate, but I just said monochlorination to signify just chlorinate once and stop. It could keep going. Just in the context of the question, it was just asking for the monochlorination product. Okay, so that's it for today. Thanks everyone for tuning in for my office hours with Chegg for Organic Chemistry 1. We're coming to you every Tuesday at 5 p.m. Pacific time, going over Organic Chemistry 1 problems. So I will see you next week for